Welcome back to Physics with Miss B, and we're moving right along into waves. Sure, we've seen waves before. We've even created our own waves, some visible and others not so visible. The most obvious waves are those produced by the ocean. They roll endlessly into the shore, then retract, producing currents that push and pull people and objects in a back and forth motion. A wave is a continuous stream of regular disturbances. These disturbances are referred to as pulses. A pulse is a single disturbance that propagates from one point to the next. A pulse can be considered a vibration. Simply put, waves that are moving transfer energy from one point to another and are classified as progressive. There are two types of waves: transverse and longitudinal. A transverse wave is one that has vibrations perpendicular to its direction of propagation, while a longitudinal wave is one that has vibrations parallel to its direction of propagation. Transverse waves can be produced by a skipping rope or slinky, by affixing one end to a sturdy point and then vibrating the free end by moving it up and down. It can also be produced by water by placing objects in them and moving that object in an up and down motion. Another example of a transverse wave is an electromagnetic wave. Examples of electromagnetic waves are light, radio, and gamma waves. Sound is an example of a longitudinal wave where you have areas of compression, where you have lots of particles clustered together, and you have areas of rarefactions where you have less particles clustered together. The parts of a wave includes amplitude, wavelength, crest, and trough. Wavelengths can travel from crest to crest or from trough to trough. Throughout this topic, we will refer to light for progressive transverse waves and sound for progressive longitudinal waves. Let's focus on the parameters of a wave: amplitude, phase, wavelength, period, frequency, speed, and wavefront. The amplitude of a wave is the maximum displacement of the vibration or oscillation from its mean position. The greater the amplitude of a light wave, the brighter it becomes, and the greater the amplitude of a sound wave, the louder it becomes. Points on a progressive wave are said to be in phase if the distance between them along the direction of propagation is equal to a whole number of wavelengths. The period T of a wave is the amount of time it takes for one complete vibration to occur. The period of the wave in the picture below is 100 milliseconds, which converted to seconds will give you 0.1. The frequency of a wave is the number of complete vibrations produced in 1 second. The frequency of a light wave determines its color, while the frequency of a sound wave determines its pitch. Frequency can be determined by dividing 1 by the period, where we have 1 divided by 0.1 seconds to give us 10 per second or 10 hertz. Similarly, period is equal to 1 divided by frequency. There are 7 colors in the rainbow: red, orange, yellow, green, blue, indigo, and violet. Red has the lowest frequency, while violet has the highest frequency. On the other hand, high-frequency sound waves are comparable to the treble note, while low-frequency sounds are those similar to a bass note. Wavefronts are generally taken through crests of transverse waves and through compressions of longitudinal waves. This is the line perpendicular to the propagation of a wave on which all points are in phase. The speed of a wave depends on the variables frequency and wavelength, where speed of wave is equal to frequency times wavelength, or the product of frequency and wavelength. The speed of light in a vacuum is 3 times 10 to the 8 meters per second, while the speed of sound in air is 330 meters per second. Sound cannot travel in a vacuum because there is no matter within it. Sound requires matter to travel, while light does not. The speed of a wave is defined as the rate at which the wave fronts of a wave propagate, and it depends on the medium of propagation. The speed of a wave can be affected by the density of a medium, examples air and glass, and the speed of a wave can also be affected by temperature and location. For example, light waves slow down when they are passing through glass, but speed up in air because atoms are more tightly packed in solids than in a gas. On the other hand, sound waves travel faster and best in solids than in liquids or gases because they depend on the vibration of particles to travel. The closer the proximity of the particles to other particles, the easier a vibration due to sound is able to transfer its energy. Sound waves also travel better in a warmer gas than in a cooler gas because the particles in a warmer gas have more kinetic energy that allows sound to travel more readily than those in the cooler gas. They also travel faster in less dense gases. Water waves are faster in deeper oceans than in the shore because a wave reaches its natural frequency in deep water, since there are practically little to no obstacles such as the ocean floor coral reefs to interrupt the movement of the water. The general wave equation is speed of the incident wave divided by the speed of the refracted wave equals to the wavelength of the incident wave divided by the wavelength of the refracted wave equal to the sine theta of the incident wave divided by the sine theta of the refracted wave equals to the refractive index of the refracted wave divided by the refractive index of the incident wave. Whew, that was a mouthful. Where v is equal to the speed of the wave in meters per second, lambda is equal to the wavelength of the wave in meters, theta is equal to the angle of the wave, eta is equal to refractive index, and 1 corresponds to the incident wave and 2 corresponds to the refractive wave. 2 important things to note are the period and frequency f of a wave do not change when they pass from one medium to the next. And secondly, if the speed v of the wave doubles, then the wavelength lambda and sine theta will double. Please note that theta does not double, it increases. Sine theta doubles. Let's try some questions. So using the picture below, A, what is the period of the wave, and B, what is the frequency of the wave? You may pause the video to try this question. A, what is the period of the wave? The period of a wave is the amount of time it takes for one complete vibration to occur. The question may be tackled like this, where a complete crest and trough are taken into consideration and the period of one cycle is determined to be 200 milliseconds, or converted to SI units of seconds, we get 0.2 seconds. Or you may try it like this, where you find the trough and you find the crest, and you're not starting from the 0 position, you're now starting somewhere in between. If you want the actual value, you would have to subtract the smaller number from the larger number to get the actual value. In this case, we have 300 milliseconds minus 100 milliseconds to give us 200 milliseconds. And then writing it in SI units, we have 0.2 seconds. Now, there are many ways in which this can be answered. Just find what works best for you. B, what is the frequency of the wave? The frequency f of a wave is the number of complete vibrations produced in 1 second. So if frequency is equal to 1 divided by period, we have frequency equal to 1 divided by 0.2 seconds, which we just computed earlier, and we get 5 per second or 5 hertz. Let's try another question. A, what is the amplitude? B, wavelength, and C, the frequency of the wave. You may pause the video to try this question. All right, so what is the amplitude? The amplitude of the wave is the height of a crest or the depth of a trough. The amplitude of the wave is therefore 2 meters, or converted into SI units, we have 0.002 meters. What is the wavelength of the wave? The wavelength of a wave is the distance between successive crests, successive troughs, or a successive crest and trough. The wavelength of the wave is therefore 40 centimeters or 0.4 meters. What is the frequency of the wave? Well, the frequency f of a wave is the amount of complete vibrations produced per second. In this case, the frequency of the wave can be determined via the equation speed of wave equal to frequency of wave times wavelength of wave, where you transpose to get frequency of the wave equals to the speed of the wave divided by the wavelength of the wave. You substitute the values that you have. Note well that we were given the speed of the wave, which was 30 meters per second. We divide it by 0.4, which is the wavelength of the wave, and we get 75 per second or 75 hertz. Here are some important notes. A. Displacement position graphs can represent both transverse and longitudinal waves. B. Pressure position and pressure time graphs always represent longitudinal waves. These waves have regions of high and low pressure, known as compressions and rarefactions. C. The mean value on the vertical axis of a pressure time graph of a sound wave is not zero. It is the value for atmospheric pressure, which is 10 to the 5 pascals, as can be viewed below. Let's try one more question. I know it's a lot. Please note that the question was adapted from the Concise Physics textbook written by Peter de Vries. Some numbers have changed in the process. This is not an original question by me, but I just felt that it was necessary to share it so that we just gain some understanding and also concrete all that we would have learned earlier. Now, a water wave has a speed of 4 meters per second and its crests are 6 meters apart. It approaches a very large reef at an angle of incidence 40 degrees. On passing over it, the distance between the crests reduced to 4 meters. A. Determine the frequency of the wave in the deeper water. B. Determine the period in the deeper water. C. Determine the frequency as it passes over the reef. D. Determine the period as it passes over the reef. E. Determine the speed as it passes over the reef. F. Determine the angle of refraction on reaching the reef. And G. Determine the refractive index on traveling from the deep to the shallow. Breathe in and breathe out. Pause the video to try this question. Okay, first of all, you want to list all the variables that you were given as are listed here. And then you want to write down some equations that you think you may need. Okay? Moving from there, we answer the question as is. So the frequency of the wave in the deeper water. We are given the velocity of the wave that is traveling in the deep water, and we're also given the wavelength. So it's best to use the speed of wave equation to solve this question, and we get 0.5 per second or 0.5 hertz. So now the next question is B, the period of the wave in the deeper water. So now that we would have solved for frequency in A, we could plug it into the period equation. Okay, so period is equal to 1 divided by frequency, and we get 1 divided by 0.5 per second, and that gives us 2 seconds. The next question asks the frequency as it passes over the reef. The frequency of a wave does not change as it moves from one medium to the next. Hence, it stays at 0.5, so therefore the wave traveling in the shallow region of the ocean will be 0.5 per second. The period as it passes over the reef. So the period of a wave also does not change as it moves from one medium to the next. Hence, the period of the wave moving in the shallow section will also be 2 seconds. So it's unchanged. the speed as it passes over the reef. So now we're dealing with the wave as it passes through shallow water, and we pick some variables where we could determine the speed of this wave moving in the shallow water. We have the frequency and we also have the wavelength. So therefore we can use the speed of wave equation, and we just substitute frequency and lambda for the numbers that we have. So we have 0.5 per second times 4 meters, and that will give us 2 meters per second. I really hope that you were able to get this answer. Now we're looking at the angle of refraction on reaching the reef. So to find the angle of refraction, we see that you can't use the speed of wave equation, and you really can't use the period equation. You need to look to the general equation. So using the general wave equation, I'm looking at the relationship between V1 over V2 equal to sine theta 1 over sine theta 2. I think that should get the answer, and it will. You just plug in the numbers as can be seen. 4 meters per second divided by 2 meters per second equal to the sine of 40 divided by the sine theta of the wave traveling in shallow water. From there, you do a series of calculations and you find the inverse of 32, and you get approximately 19 degrees. The final question states that it would like you to determine the refractive index on traveling from the deep to the shallow. Again, you look for a relationship that will be easy for you. I took V1 over V2 equals to eta 2 over eta 1. So I felt like that relationship is okay since I would have V1 and V2. I stick those values in and I was able to get 2. I really do hope that you also got these answers. Alright guys, I'd like to thank you for watching another session of 30 Days of Physics with Miss B. See you for the 21st day. Bye.